Well, hi, welcome to this third video of the Future Internet course. This we will continue with the SDN topic, and we will talk here about the control and data planes separation. So, in the agenda of these slides, we're going to have first, what is control and data plane separation? Why is it a good idea? And what are the opportunities and mainly the challenges that entail this separation of the data plane and control plane? And finally, in the end, we will talk a little bit about OpenFlow, which makes possible this separation between control and data plane that we already talked a little bit about in the previous videos. Material is from the SDN Coursera course of Professor Nick Finster. You can go to the link to find the more of the original material. So first of all, again, and we will talk of this again, what are the control and data planes, right? So let's remember a little bit what we said in the last videos. So control and data planes are different because in the control plane we have the logic for controlling the forwarding behavior. Remember, the control plane is like the brain of the network, and is there where we actually calculate the forwarding state. So, for instance, we can think of the control plane as the routing protocols, as the security, let's say, algorithms, and all the intelligence in the network that is used to calculate the decisions that the network will take in terms of routing, traffic engineering, security, and so on. In terms of the data plane is the one in charge of just forwarding traffic according to the control plane logic. So there we have the IP forwarding or the layer 2 switching. So there in the data plane we have like the routing tables or the switching tables, flow tables, where depending of the information of each packet arriving to the switch or the router, we take the decision on to forward the packet or store the packet or reject the packet or discard the packet and so on. And these decisions are made taking into account the logic that the control plane installed in this data plane. So it's very important again to have this differentiation very clear. But why should we separate the control and data planes? We already talked about this in the previous video. This is just a reminder. We need an independent evolution and development of concerns. So if we can separate the control and data plane and not put them as we have it in the traditional way, we can evolve the control plane just as a software evolution. So we will not depend on the manufacturers or on the hardware. So we will create control plane applications, algorithms, and so on that can be just evolved as a software plane. So it will follow the software evolution. Also, we can have a control from high-level software programs. So the control plane will be just a software program or a set of applications which will define the control behavior using just high-level programs, right? In this way, we can also debug and check the behavior of the network in an easier way. Let's talk a little bit about the opportunities where this separation helps. For instance, in data center, we will see two examples, the VM migration or the layer 2 routing. In the routing, we can have more control over the decision logic, and we can even evolve new routing algorithms depending of the needs of the customer. In the enterprise networks, in terms of security applications, this will also help a lot in security, as having the security in a centralized plane. And in the research networks, because of the coexistence with production, so we can having a control plane can have let's say an experimentation a part of the network used just for experimentation, and this can be coexisting with production. So every new experimentation that we do, we can deploy it immediately in the production network. So these are very good opportunities. However, we have to continue challenges. The scalability, very important, because if we just have one control element, remember that the control plane will be just located in servers. So if we have just one control element, one server for to perform the control of the network, it will be responsible of many forwarding elements, often thousands of elements. So it's very important to have the scalability in mind. The reliability and security. Also, if we have just one, for instance, controller, what happens if it fails, or if it is attacked? So then the whole network will go down. So how to deal with these two challenges? We're going to see something of that in this video or in the next one. So let's just talk a little bit about two different opportunities that we can have the separation of control and data plane. For instance, in data centers, cost and management. Let's think on a data center that have 200,000 servers, and the fan out of each switch needed to deal with all the servers is 20. So in this case, we need 10,000 switches. And let's think that we have a vendor of a traditional switch of $5,000, for instance. So in this case, we will need $50 million to cope with all this, the costs of the networking in the data center. But let's think that we don't need a special traditional switch that knows all the protocols and so on, but we just buy a commodity switch where you can install your control programs by means of SDN, by means of the separation of control and data plane. Of course, also those switches are going to be a lot cheaper because they will not have all the, let's say, complexity and protocols installed of the traditional switches. So they can be around $1,000. So it's $10 million, and the savings can be of $40 million in one data center, or $400 million in 10 data centers. That in this money can be used then to build or to hire programmers to program the control plane that is actually customized for the network that you need. This is the idea. Another application that is very interesting is the data center addressing. So for instance, traditionally or normally, what you have in a data center in general, in a local area network, is a layer 2, right, with the MAC addresses of the servers and so on, and a layer 3. And in layer 2 routing, for instance, you need less configuration and administration because it's just MAC addresses, but very bad scaling properties, because when you are sending information in this way, in layer 2, what you have is normally the need to send broadcasts to the network, because you don't have a routing hierarchy as you have in layer 3. In layer 3, of course, you can use the routing hierarchy with routing protocols, but it has high administration overhead. So how to get the best of these both worlds? We can do something with SDN. So think on a data center where you have a separated controller. We call the controller fabric manager here. This is just a controller or a control plane separated from the data plane, right? And then in this controller, we have the information of the network. So let's think on this data center where this is first tier of switches, then this is the second tier of switches, and here you have a third tier of switches. And what this does is to organize the routing, to have a hierarchy in routing in terms of the MAC address. So let's think that this host has a normal MAC, what we call here this MAC, actual MAC address, but every time this host sends a packet, the Fabric Manager has a mapping between the actual MAC and something called a pseudo MAC. And this pseudo MAC will have the information of the location of the host. So for instance, if the host is in this part of the network, it will have the pseudo MAC that you can see here, 0001, 020001. So you can have like the separation of networks in the pseudo MAC. Let's say that the network of these 4 hosts will be the, I don't know, 0200, and then each host will have its own address, 01, 02, 03, and 04. And in this way, all switches will be controlled by this controller or Fabric Manager, and will know when a packet is sent to a switch, to a host inside the network. They don't have to send a broadcast to see where the host is, or they don't have to use layer 3 routing. They know by the pseudo MAC we configure here in which part of the network this host is located, and can make the routing in this way. Can intercept all the ARP packets, assign new end hosts with pseudo MACs, and then you can rewrite MAC for packets entering and exiting the network. Each time a packet enters the network, you will, the switch will rename the packet destination with the pseudo MAC, and with the pseudo MAC, they already have in the switch tables how to route this packet, because they know where the packets are located, the hosts are located in the network. And if the packet is exiting the network, then it will change the pseudo MAC with the normal MAC, and it will just exit the network. So this is more or less the idea of this, let's say, new layer 2 addressing taking into account hierarchy with SDN. There are a lot of more opportunities regarding this. For instance, using SDN, dynamic access control, seamless mobility and migration. This is very important. You can do a seamless migration in mobility by passing from, for instance, one access point to another access point. Will be transparent for the user. The user will not see anything in the performance of the application. Using SDN, you can do server load balancing, network virtualization, which is something very important we will talk about later. Using multiple wireless access points for just one user, energy efficient networking, adaptive traffic monitoring, DDoS attack detection with SDN, and a lot of more opportunities and applications that you can see from the separation of control and data plane. There are a lot of challenges, though. So we have scalability, reliability, and consistency, routing decisions for many routers, correct operation under failure, consistency. And in the next video, we will see how to solve this problem using 2 controllers or control plane alternatives that have been proposed, are the RCP and ONIX. We will see this in the next video. The RCP and ONIX papers are here. In the next video, we'll talk about how to solve these challenges with these controllers. Thank you very much.